Okay, we're going to talk about rationalizing denominators now, which means we want to make the denominator a rational value. Right now, in this first example, it says 1 over radical 2, or the square root of 2. So this value right now, the square root of 2, is irrational. Square root of 2 is irrational. And if you remember, it's irrational because if we do the square root of 2, it'll be a non-terminating decimal that has no specific pattern. Right? So it'll just be a decimal that goes on and on forever, kind of like pi. So we want to make this a rational value. So in order to do that, since this is a square root, if I had a perfect square underneath there, I would be able to simplify it, right? If that wasn't a 2, but instead was a 1 or a 4 or a 9, what do we have, 16, 25, dot, 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 right? If it was a perfect square, we would be able to simplify it. So what we want to do is we want to make it a perfect square. What could I multiply radical 2 by to make it a radical 4, for example? So I could multiply radical 2 times radical 2, and that would give me radical 4. But I can't just multiply the bottom by radical 2. It would change the value of the fraction. So what I have to do is I have to multiply the top also by radical 2. This does not change the value of the fraction because radical 2 over radical 2 is just 1, right? And anything times 1 is itself. So we're creating an equivalent fraction. So radical 2 times radical 2 is radical 4, and 1 times radical 2 is radical 2. So now I have the square root of 2 over the square root of 4. Now we already discussed that there is no square root of 2. We can't simplify that. But we can simplify the square root of 4. The square root of 4 is 2. And we've rationalized the denominator. The denominator is now a rational value. The numerator isn't, but that's not what we're concerned with. Right? We're concerned with just rationalizing the denominators in this section. So let's try some more examples. So here's three more examples we could try. If you want, you could pause this video and try working on them. Otherwise, I'm just going to start right away. I have 2 over the square root of 7. So what I want to do here is I want this to be a perfect square. So I want to multiply the numerator and the denominator by 7. Right? Because then I would have 7 times 7. This will give me the square root of 49, which is a perfect square. And up top, I'll have 2 radical 7. And this could be simplified, so I'm going to have 2 rad 7 over 7. In this next example, I have the square root of 5 over 3. So that's really equivalent to the square root of 5 over the square root of 3. I could break that up, right? And then I want to get rid of this radical 3. So what I'm going to do is I'm going to multiply the denominator and the numerator by radical 3. So I'm going to have a radical 15 all over radical 9, which is rad 15 over 3. And in this next example, I'm going to multiply the numerator and denominator by rad 5. So I'm going to have 2 rad 15 all over rad 25. So I'm going to have 2 rad 15 all over 5. Square root of 25 is 5. If this could be simplified, we would. If we could cancel out, we would. I put one more example down here, 5 over the square root of 8. So there's two places we could do, we want to rationalize this 8. So typically you might be drawn to saying, well, 8 times 8 is 64. We could do it that way. But an easier way might be able to recognize that 16 is a perfect square. So if I multiply the numerator and denominator by radical 2, right? 8 times radical 2 will give me the square root of 16, and 5 rad 2 up top. So it looks like I'm going to have 5 radical 2 all over 4. It would have been fine if you did 8. It just would have been a longer process. If I do 5 over rad 8, and then I multiply the numerator and denominator by rad 8, I would have 5 rad 8 over radical 64. So I would have 5 rad 8 over 8. And then we would have to simplify this radical. So really I would have 5 times radical 4 times 2 over 8, which would be 5 times 2 rad 2 over 8, which would be 10 rad 2 over 8. And then you would have to simplify this, 5 and 4, and we'd end up with the same answer. So you could see how much work we saved by just multiplying by a 2, right, to keep this down to the smallest perfect square as possible. Those examples are fine for square roots. So as a rule of thumb, all you need to do is multiply the numerator and the denominator by whatever's in the denominator. So it's pretty simple. But if I have cube roots or fourth roots or fifth roots, it's a little bit more complicated. In this first example, I have 1 over the cube root of 2. Well, as soon as I have cube roots, it's a good idea to remember what my perfect cubes are. 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, 5 times 5 times 5. So these are perfect cubes. So I want to keep that in mind. So what I want in this denominator is I want this denominator to be a perfect cube. I want it to be one of these values. So what do I have to multiply it by in order to be one of those values? 2 times what value will give me 1? Well, that's going to be tough. 2 times a half, I guess. But this looks like a good one right here. Right? I could make a 2 into an 8 by multiplying the numerator and the denominator by rad 4, or the cube root of 4. So I'd have 2 times the cube root of 4, which is the cube root of 8, and 1 times the cube root of 4, which is the cube root of 4. So now I have the cube root of a perfect cube, so I'm going to have the cube root of 4 all over 2. Try another one. Here's 2 over the cube root of 3. So again, we want this 3 not to be a 3 because it doesn't fall into my perfect cubes. I want it to be a 1, an 8, a 27, 64, 125. So what can I multiply it by to become one of those? Well, I know 3 times 9 is 27. So I can multiply the numerator and denominator by the cube root of 9. And that way I have the cube root of a perfect cube. Whatever I do to the bottom, I have to do the same to the top. So I have 2 times the cube root of 9 up top. I could simplify this. Cube root of 27 is 3. So I have 2 cube root of 9 all over 3. In this next example, I have a denominator with a variable. So this is a little bit trickier, right? So we could look at this a few ways. Well, I want to multiply, this is a square root, so I want this to be a perfect, the result multiplying by a value where the result I want to be a perfect square, right? I want this 3 to be a perfect square. I know 3 times 3 is 9, and that would be a perfect square. And if this is x to the first, I want to multiply it by x to the second, because that would result, oops, I take that back. I want to multiply this by x to the first, so that way I'm left with x to the second. I want a perfect square. My mind was still with those cubes for a second. So I want to multiply the denominator by rad 3x, and I want to multiply the numerator by the square root of 3x as well. So I'm going to have the square root of 21x up top, and on the bottom, it's a perfect square. Square root of 9 is 3. The square root of x squared is x, and up top, I'm left with 21x. So if I have a variable, you want to be careful, because if it's a square root, it has to be a multiple of 2 to be a perfect square. If it's a cube root, it has to be a multiple of 3 to be a perfect cube, and so on. If it's a fifth root, it has to be a multiple of 5. The exponent would have to be a multiple of 5 to be a perfect fifth root. Let's look at binomial denominators. If the denominator is a binomial, has 2 terms, and has radicals in it, or a radical in it. In this case, what we want to do is, what we need to do is multiply by the conjugate, which we discussed what a conjugate was. The conjugate of the denominator. Since we're rationalizing the denominator, our focus is on the denominator only. So in this case, if I wanted to multiply by the conjugate of the denominator, my denominator is 3 plus radical 7. So the conjugate would be 3 minus radical 7. And again, whatever I do to the denominator, I have to multiply the numerator by the same thing, because 3 minus radical 7 over 3 minus radical 7 is equal to 1. So it doesn't change the value of the fraction. All it does is create an equivalent fraction. So we could do this multiplication. We could distribute up top. This would be 3 times 3 is 9, minus 3 times radical 7 is 3 times radical 7. On the bottom, since these are conjugates, you could FOIL this all out, right? We could distribute all over the place. But since we know they're conjugates, we just need to multiply the first with the first, which is 9, and the last with the last, which will give me the subtraction of 49, right? The square root of 49 there. So it looks like I'm going to have 9 minus 3 rad 7 all over 9 minus 7, which is 9 minus 3 radical 7 all over 2. And we rationalize the denominator. Success. In this example, the binomial has 2 radicals in the denominator. That doesn't make a difference. Again, we're looking to rationalize the denominator. So all we need to do is multiply the denominator by the conjugate. So we're going to multiply by rad 7 plus radical 3. Right? And whatever I do to the denominator, I have to also do to the numerator. So that way this value is equivalent to 1. And then I could distribute. So I would have 11 rad 7 plus 11 rad 3 all over, well, this is going to be radical 49 plus, minus radical 9. right? And then you could take the square root of both sides. Right, so I'm going to have 11 rad 7 plus 11 rad 3 all over 7 minus 3, which is 4. We could skip some steps, but I don't want to skip any steps. I'll let it get into focus there. So we distribute. Sometimes the book doesn't distribute. Sometimes the book writes this as 11 times 7 plus rad 3. Sometimes they leave it in that form. Whatever. Either way is fine with me, but the denominator has to be simplified, and that's what we have there. The reason they do this is if I had this all over 4, that's fine. But if I had it all over 11, it would be easy to cancel it out, right? If there was a common factor up top, that could be simplified. So it does make sense, you know, as far as simplifying it later on. But that's it for rationalizing denominators. When they are binomials, we just multiply by the conjugate. Easy stuff. The last topic covered in this section is fractional exponents, which are kind of scary looking, especially fractional negative exponents could be scary looking. But fractional exponents are just radicals. It's just another way of writing a radical, a square root or a cube root. The way you want to think of this is the denominator is the root, and the numerator is the power or the exponent, right? I always remember it like on a tree, right? The root is on the bottom and the power is on the top. So the root is on the bottom. So this would be written as the cube root of 8 to the second power. It would be equivalent to the cube root of 8 to the second power. And then we could simplify that, because I know the cube root of 8 is 2. So this would really be 2 to the second power, which is 4. Now, I wrote cube root of 8 and I wrote the 2 on the outside, but what if I said it's the cube root of 8 to the second power? Right? My root is my index and my power is my exponent there, or the numerator is my exponent. Would that be equivalent? Does it make a difference if I write it out there inside here? Let's see. So this would really be the cube root of 64, and the cube root of 64, 4 times 4 times 4 is 64, so it works. So you could have it outside or you could have it inside. It's not going to make a difference. I like it outside because then it's smaller numbers to deal with. I'd rather take the cube root of 8 than the cube root of 64. Let's move this down a little bit. I should move the camera. So here, if we look, this could have been done on your calculator as well, but I don't want you to get too comfortable with using your calculator, because when we have variables like x and y, you're not going to be able to simplify using your calculator. But if you wanted to do this on your calculator, it could be done. Simple values like that. I also want to show that anything, just to reiterate, that fractional exponents are radicals. Right? If I have 25 to the 1/2 power, well, like I said, that's my root. So this is the square root of 25 to the first power. So this is just another way of writing the square root of 25. Right? 25 to the 1/2 is just the square root of 25. And the same thing here, right? this is my index, so this is the cube root of 8 to the first, right? So the cube root of 8 is 2. And this is the fourth root of 81, which is 3, and this is the fifth root of 32, which is 2. So this is another way, if I had to find the fifth root of 32 on my calculator, back a long time ago when my calculator wouldn't do fractional exponents, or rather, my calculator I couldn't do anything other than a square root on my calculator back in the early 80s. So I would have to plug it in. If I want to do the fifth root of a value, I would have to write it as a fractional exponent. I had the caret function, but I didn't have the ability to change the root. So I would always have to, if I had this problem, I would have to input it in my calculator like that, back in the old days. Here we have 7 more examples for you to try. So you could pause the video now and try working on these, or you could watch me work these out. In this example, I have 121 to the 3/2, so that's the square root of 121 to the third power. And I know the square root of 121 is 11 to the third power, which I would have to pull up a calculator, because 11 to the third power is kind of big. I believe it's 1,331. I wouldn't give you anything that big. But even if I did, you have a calculator, you could do 11 to the third. But if you had a calculator, you could do it this way as well. In this example, the cube root of 27 squared. The cube root of 27 is 3. Squared would be 9. In this example, excuse me, I have the fourth root of 81, all to the third power. And the fourth root of 81 is 3 to the third power, will give me 27. Here I have the fifth root of 32 squared, and the fifth root of 32 is 2. 2 squared is 4. I kind of squished these in here, but I have some negative fractional exponents, which look challenging, but they're very doable. Here I have 16, or rather the fourth root of 16, all to the -5. And the fourth root of 16 is 2. 2 times 2 times 2 times 2, 16. 2 to the -5th. So 2 to the -5th is really equivalent to 1 over 2 to the +5, which would be 1/32. Right? Negative exponents have to come to the bottom. Similarly here, I'm going to have, it looks like the square root of 9 to the -3. So it's really 3 to the -3. Right? Negative exponents have to come to the bottom, so it's 1 over 3 to the +3, or 1/27. 3 times 3 times 3 is 27. And in this last example, we have the fifth root of 32 to the -1 power. And the fifth root of 32 is 2 to the -1 power. So this has to drop to the bottom. It would be 2 to the +1 power. So our final answer is just 1/2, right? 32 to the -1/5 is 1/2. So let's try some more challenging ones. some with variables. So this example says 7 cube root of x times 2 fourth root of x. So since we haven't learned any properties of radicals to multiply or anything like that, at least not when the indexes are different, but we do know that these radicals are really the same as fractional exponents. And we have a lot of properties for exponents. So why don't we write this in exponential form? Right, this would really be 7x to the 1/3 times 2x to the 1/4. And I know 7 times 2 will give me 14. And I know when my bases are the same, I add my exponents. What's 1/3 plus 1/4? A lot of people have a problem with this, 1/3 plus 1/4. What's 1/3 plus 1/4? 7/12. I believe it's 7/12. So it would be x to the 7/12. You want to know how I got 7/12 real quickly? Well, 1/3 plus 1/4, a cheating way or a shortcut way of adding fractions, we could just multiply the denominators. That'll give me 12. And then I cross multiply from the bottom up. 4 times 1 is 4. 3 times 1 is 3. So this would be 4 plus 3. That's where I'm getting 7/12. Will that work with subtraction? Sure, it'll work with subtraction. Just to do a quick example, if I had, 2/3 minus 1/2, I would multiply my denominators, so that would be 6. This is going to be 4, and this is going to be 3. 3 times 1 is 3. 2 times 2 is 4. I'm subtracting 1/6. So 2/3 minus 1/2 is 1/6. An easy way to add and subtract fractions. In this next example, we're happy with that answer. Let's write it in radical form. Since it was given to us as radicals, maybe we should give the answer back as a radical. So this would really be 14/12 root of x to the 7th. In this next example, it says the cube root of the square root of x. Again, if we're going to follow the same thought pattern, I don't want to have different indexes like this. I rather have different exponents. So this is really going to be x to the 1/2 all raised to the 1/3. Right? That's what's going on here. And I know my properties of exponents. When I have a power raised to a power, all I have to do is multiply these. And 1/3 times 1/2, all we do is multiply straight across. So we'll get 1/6. So this is equal to x to the 1/6, which in radical form would be the 6th root of x. In this section, they also ask you to reduce the index. So really, when you reduce the index, let's think about it logically. If I think about this fractionally, right, reducing makes me think of fractions anyway. So this is really 6/9, right, which could be reduced. 3 goes into the top and the bottom. So it would be x to the 2/3. So this looks like it's going to be the cube root of x squared, right? The cube root of x squared. Now, all of this, for me, is just a way to think about it. But in reality, we could look right here, and we know this is a fraction, 6/9, and we could reduce it right here. Instead of saying 3 goes into the numerator and the denominator, we could say 3 goes into this exponent and this index, and we could have reduced it right here. We could have skipped all this and moved right to there. If we divided this by 3 and this by 3. So similarly, we could see that 4 and 12, this one's a little funny because it's going to be, let's do it as a fraction. This will be x to the 12 fourths, which is x to the third, which is not a fractional exponent, that's the end. If I were to reduce it, I would see we would have an index of 1, x to the third, which is just x to the third. Right, if I divide both of these by 4, I would have come up with the same thing. In this problem, I know the index and the exponent are both divisible by 2. So this would be equivalent, I'll write it over here, to the square root of 7, right? 7 to the first power. And if we wanted to write it as fractions, this would be 7 over 2 fourths, which is 7 to the 1/2, which would bring us to the same place. And lastly, 12, 4, and 8 are all divisible by 4. So I could divide them all by 4. So this would really be the cube root of x to the first, y to the second. And that's how we reduce indexes. In this section, they also have some exercises on using your properties of exponents, but in this case, they give you fractional exponents. So, for example, if they gave you 3x to the 2/3 times 4x to the 3/4, and they said simplify using properties of exponents, well, we know that we multiply our coefficients, so this would give us 12. My bases are the same, so I add my exponents. So this is going to give me, let's say I multiply my denominators, I get 12. 4 times 3 is 8. 8 plus 9, this looks like 17/12. 12x to the 17/12 would be my answer. And let's do 3 more. Oops. Again, if you want to pause it, this would be a good time to pause it and try these problems. So in this next example, this looks like a division problem or a quotient property here. We want to do 72 divided by 9, which is 8. And then I keep my base and I subtract my exponents. So I have a 3/4 minus 1/3, which will give me 12 on the bottom, 9 minus 4. 5/12, x to the 5/12. Right, if I keep my base, I subtract my exponents, that looks like my final answer. They said use properties of exponents, so they're not asking you to do this in radical form. And anytime an example is given to you in a specific form, usually that's the way you want to give the answer back. So they proposed this question in exponential form, so I gave my answer in exponential form. Before they gave the example in radical form, so we give our answer in radical form. For this one, I have a power raised to a power, so I take my exponent on the outside, I multiply it to the exponents on the inside, so it's 125 to the 1/3 power. X, well, I guess if you want to write it to the 9/3, and and y to the 6/3. Right, if I multiply 9 times 1/3, just so you know where I'm getting that from, is 9/3, right? It's 9 over 1. So now when I simplify this, this is really the cube root of 125, which is 5. 9 over 3 is 3, and 6 over 3 is 2. So if I reduce those fractions, I end up with 5x cubed plus y squared. And in this last example, it looks like a little of everything. We're going to distribute. So I'm going to have 2 to the 4th and y to the 4/5 all over y to the 3/10. Well, 2 to the 4th is 16. And then here my bases are the same, so I'm going to subtract my exponents. 4/5 minus 3/10, well, we could do this a few ways. 4/5 is really the same as 8/10. So really I have 8/10 minus 3/10, which is 5/10, which could be reduced. This is 16y to the 1/2. And that's it. Everything you needed to know about roots and radicals.